Hello and welcome to this revision class on PM2B. What I will cover today is some content of our lectures. There were 12 lectures in total. I delivered in the autumn term and also in spring term. And these lectures initially included lectures on polymers. So in the first lectures I introduced you to polymers and their properties. Then I talked about polymers in solid state and covered a bit about the synthesis and modification of polymers. Then lecture number 3 was about polymers in solutions, how they dissolve and then how they behave in solutions. The following lecture was covering polyelectrolytes, the charged polymers, and how they behave in solutions. And specifically, I was talking about viscosity and gelling properties, as well as rheology of polymers. Then, starting from lecture number 5, I started covering the content on the application of these materials, and not only polymers in this case. Lecture number 5 was focused on mucoadhesive dosage forms. Then lecture number 6 and 7 were covering the hard capsules and soft capsules. Then lecture number 8 was focused on oromucosal drug delivery. And number 9 was on rectal drug delivery. Then number 10 and number 11, these two lectures covered the oral modified release and various coatings and various other materials that are present in coatings. And lecture number 12 was focused on sterilization. So as you see, there's a lot of material to go through, and obviously during this revision session I will not go through all the content of the lectures. What I decided to do, I decided to prepare a summary highlighting the most important points and highlighting the things that you're supposed to know. Okay, let's move on. Right, so what you're supposed to know about polymers. First is special properties of polymers, the properties that are typical only for polymers. And there are 5 types of these special properties. First is the aggregate state. To remind you that polymers cannot exist in gaseous state. They could be solids, they could be liquids, but they cannot be gases because they have too large molecular weight, so their molecules cannot fly. Second, because the polymers, their molecules are very large, they are macromolecules, then they have a specific feature when they dissolve. In order to dissolve, polymers first must swell. Why it happens? Because water or any other solvent, their molecules could diffuse into the structure of a polymer. Then this polymer material becomes swellable, it swells, and once it's swollen, the macromolecules become more mobile, so they could diffuse out of a sample of a polymer. Only then they could dissolve. So before the polymer dissolve, it will swell. Once the macromolecules are fully in solution, again, because they're very large, so the solutions of polymers, they typically will be much more viscous compared to solutions of small molecules. In solid state, polymers also have very special properties in terms of their mechanical behavior. You're familiar with many plastic materials, especially rubber, and you are familiar with the ability of rubber and even other plastics to undergo so-called reversible deformations. So we could stretch samples of polymers, and when we apply force, but once we remove this force, they could come back to their initial state. And this mechanical property is quite unique for polymers. Also, polymers in solid state could behave differently to the materials composed of small molecules in solid state. Many small molecules in solid state, they will have a tendency to crystallize, and sometimes it is difficult to make them more amorphous. For the polymers, it's the opposite. Polymers will have a tendency to form amorphous solids, and they will practically never form 100% crystalline materials. Some polymers could be only fully amorphous. Some polymers could be semi-crystalline, so within their structures we will be able to observe the presence of some amorphous areas and also some crystalline domains where there will be a bit of crystallization. And again, this is very typical for polymers to form amorphous solids. Why it happens? Because polymers are very large macromolecules, and it is extremely difficult for each macromolecule to arrange into a certain packaging to ensure that it forms crystalline structure. What you're supposed to know when you will be revising for this exam, you're supposed to know the important definitions in polymer science. I don't expect you to memorize all the definitions, but as long as you have understanding what each term means, and to list these definitions, well, we will go through them in a second. So what you're supposed to know the difference between monomers, oligomers, and polymers. Obviously, polymers are large macromolecules, but polymers are made from monomers, from small molecules that could be polymerized. And intermediate stage between the monomers and polymers are so-called oligomers. The difference between oligomers and polymers is in their molecular weight. So when the molecular weight of the molecules is very large, if we will be adding like 1 or 2 additional repeating units to their macromolecules, and if this addition will not make any changes to the physical properties of material, then that will be a polymer. But for oligomers, oligomers could be composed of 2, 3, 4, 5 or a few more molecules of monomers, and every addition of the repeating unit will actually change the properties. In this case, if the properties are getting changed, then this will be classified as oligomer. But then when the properties are stopped getting changed, then this will be already a polymer. Then polymers, they consist of macromolecules. So molecules of polymers, they are called macromolecules. Sometimes they are also referred as polymer chains. So basically macromolecules and polymer chains is the same thing. Each macromolecule or polymer chain will consist of elementary unit or elementary repeating unit, and this will be like a molecule of monomer, a repeating unit of a monomer that will repeat itself along the macromolecular chain. Then, because macromolecules are still molecules, even though they are quite large, but they will always have some end groups, or sometimes they are referred as terminal groups. The number of repeating units in a macromolecule will be defined as the degree of polymerization, and the molecular weight of a macromolecule will be the molecular weight of the whole macromolecule. Then macromolecules of polymers, unlike small molecular weight compounds, they may not be exactly the same in their chain lengths and their molecular weights. Each sample of a polymer will possibly include macromolecules of different chain length. Therefore, this system will be polydisperse, and polydispersity is defined as the ratio of two values, so-called weight average molecular weight and number average molecular weight. Also, the chemical architecture, the architecture of macromolecules will be defined as their configuration. Configuration of macromolecules cannot be changed unless you are breaking the chemical bonds. Also, there are different types of configurations. For example, macromolecules consisting of repeating units of the same kind will be called homopolymers, and macromolecules consisting of repeating units of two kinds will be called copolymers. Polymers in solid state, they have a very specific a number of specific properties. They could exist as semi-crystalline and as amorphous. Also, amorphous polymers, they have three physical states, which is glassy, rubbery, and liquid. You may remember the curve showing the transitions between the glassy, rubbery, and liquid polymers, which is typical for amorphous materials. What you need to know also is the definition of glass transition temperature, which is the temperature in between the glassy state and rubbery state. Temperature above if you are heating up the polymer, then above glass transition temperature, the glassy polymer becomes rubbery. Then you also need to know about the behavior of polymers below and above glass transition temperature. And also, you should be familiar with plasticization as an effect of different small molecules on glass transition temperature. So plasticizer, when it is added to polymers, it will reduce glass transition temperature, which may make the material softer. Polymers could be synthesized by different ways. There are a number of ways of making polymers from small molecules, depending on the structure of these small molecules. So molecules with double bonds, they could be polymerized using so-called addition polymerization. Molecules with at least two functional groups, they could undergo step growth polymerization or polycondensation. Molecules of cyclic nature, but not all of them, but some cyclic molecules, they could undergo ring opening polymerization. And sometimes we could make new polymers by chemically modifying the existing polymers. Some polymers could not even be made by polymerization because their monomers are unstable, but sometimes we could take polymers of one kind, modify them chemically, and we could produce polymers of a different kind, or we could take polymers from nature and we could modify them and we could prepare polymers of a different kind. You're also supposed to have good understanding of the factors affecting the solubility of polymers. There are several factors that you need to know. The first factor will be polymer-solvent interactions that will be dependent on the chemical nature of both polymer and the solvent. So if there's a structural similarity between the solvent and the polymer, then potentially the solvent will be able to facilitate dissolution of the polymer. For example, more polar polymers will be more soluble in polar solvents, and non-polar polymers will be more soluble in non-polar solvents. Presence of crosslinks or strong intramolecular interactions could potentially affect the solubility. Typically, if there's crosslinks present within the polymer, then this polymer will not be able to dissolve, and maximum what it could do, it could swell in a solvent. Also, strong intramolecular and intermolecular interactions between the macromolecules could also act as the crosslinks, but this time will be called physical crosslinks. Molecular weight of macromolecules could also affect the solubility. Polymers of larger molecular weight will be less soluble, polymers of smaller molecular weight will be more soluble. And also temperature. Temperature has a very unusual effect on the solubility of polymers in a way that it could be different types of polymers whose solubility could either improve with increase in temperature, or sometimes whose solubility will be deteriorated with the increase of temperature. There's several classes of these systems, and in the lectures I covered the examples of polymers with so-called LCST, low critical solution temperature, and UCST, upper critical solution temperature. Also, in my lectures I gave you examples of different polymers, specifically water-soluble polymers, and I also highlighted those polymers that you need to memorize, the structures of the polymers you need to memorize. So this slide summarizes some examples of water-soluble polymers, polymers that are soluble in water, and all of them are non-ionic, so they don't have ionizable groups. And the structures you need to memorize are the structures of polyethylene oxide, or sometimes it's called polyethylene glycol. Second one is polyvinyl alcohol. Third is polyacrylamide. And fourth is poly and vinyl pyrrolidone. So these four structures you need to remember. Also, some water-soluble non-ionic polymers could be represented by more complex macromolecules, for example by block polymers, and one of the commercially important, commercially available examples, and this polymer is used in pharmacy, is a series of polymers called pluronics. Pluronics are tri-block copolymers of polyethylene glycol, polypropylene glycol, and polyethylene glycol. Pluronics are commonly used in many pharmaceutical formulations. One special class of polymers we considered is called polyelectrolytes, and polyelectrolytes are defined as polymers having ionizable functional groups, which means that in their macromolecules some charged groups could be present. Depending on the types of charged groups present in the macromolecules, they could be classified into three types. They could be cationic or polybases. In this case, the macromolecules will have positively charged groups. They could be anionic or polyacids. In this case, they have negatively charged groups. But if within one macromolecule you will have both positively charged and negatively charged groups, then these polyelectrolytes will be called amphoteric or polyampholytes. And to give you some examples, for example, anionic polyelectrolytes, it could be polyacrylic acid, is another polymer that whose structure you need to memorize. It has carboxylic group. Carboxylic group could dissociate and could give negatively charged group. Then cationic polymers, for example, polyethylene imine, again another polymer to memorize. It has an H group, secondary amine, that could be protonated and could become charged. Or another example, another very important example is chitosan. Chitosan is a polysaccharide of cationic nature. It has amino groups, NH2. These amino groups could be protonated according to this scheme, and this gives the chitosan macromolecules charged groups, which are NH3 plus groups. Also, amphoteric polymers. Example of amphoteric polymers, well, any protein is amphoteric, and denatured proteins are amphoteric. So they have both positively and negatively charged groups. One of the examples that is very important for pharmaceutics, for pharmaceutical application, is gelatin. Because gelatin has very complex structure, you don't need to memorize the whole structure. Nobody remembers the whole structure, nobody remembers it for the gelatin, but schematically you could draw it like that: wiggly line and carboxylic group and NH2 group. That will be a good example of amphoteric polymer, when you have a polymer with some negatively charged groups attached and positively charged groups. Also, what is important to know that specifically for amphoteric polymers, you have a special property that is called isoelectric point. So you should have an idea what is the definition of isoelectric point. Isoelectric point is a pH at which the amphoteric polymer will have a total charge of 0. Because depending on pH, amphoteric polymer could be either positively charged or negatively charged. But at some intermediate pH, which is isoelectric point, this polymer will be no charge, will have no charge. Next thing what you need to know about the polymers is the special phenomenon that is called conformation. Conformation is basically a shape of macromolecules in solution. Once the polymer is dissolved, then the macromolecules will acquire specific conformation. And there are several types of conformations. For example, globule, when the macromolecule is very compact, is very compactized. Then coil or statistical coil when the macromolecule is swollen in a solvent. Some specific macromolecules, for example rigid chain polymers, could have a conformation of rigid rod, and some biopolymers could have a helical conformation of helix. Typically, conformation will depend on the chain flexibility and also on polymer-solvent interactions. Then in one of the lectures I introduced you to the rheology, a science of liquids flow, and I did talk about the Newton's law when the certain fluids, so-called Newtonian fluids, could obey the linear relationship between the shear rate and shear stress. Any deviation from this Newtonian flow behavior will be defined as non-Newtonian flow, and these fluids will be called non-Newtonian. There are several types, for example, simple plastic flow, simple pseudoplastic flow, and dilatant flow. And different types of semi-solid dosage forms could be defined as non-Newtonian. Well, one of the examples is a toothpaste that does exhibit dilated flow. And also, if you remember, there was a nice video showing the behavior of non-Newtonian fluids. Then in the next lecture, I covered mucoadhesive dosage forms. What you're supposed to know is the definition of mucoadhesion. Again, mucoadhesion is defined as attractive interactions between the dosage form and mucosal surface in a human body. Then you need to have an idea about the current routes of mucosal administration, which will include the ocular, nasal, oromucosal, oral, vaginal, gastrointestinal, rectal, and intravesical. Intravesical is drug delivery to the bladder. Then you should be able to discuss the advantages of mucosal routes of drug administration. For example, one of the advantages is the ease of application and also ease of termination of therapy. Then possibilities for targeting specific organs, tissues in our body. Then avoidance of some metabolic effects related to gastrointestinal transit, for example, for non-oral applications. And there are some other advantages. Also, you need to have an idea about the methods of testing the mucoadhesive dosage forms in vitro and in vivo. There are a number of in vitro techniques. We discussed some techniques which use the special device measuring the detachment forces of a dosage form from a freshly excised mucosal tissue taken from animals. This is called tensile test. There's also a flow test that could be used when you will put a formulation on an animal mucosal tissue. You wash it with an artificial body fluid and you monitor how much of the formulation stays on the tissue. Or sometimes in vivo techniques could be used. For example, some laboratory animals could be used to test the retention of dosage forms or adhesion of dosage forms. Types of materials with mucoadhesive properties. The majority of mucoadhesive materials they belong to polymers. There's some exceptions. Some non-polymeric materials also could exhibit mucoadhesion, but the majority of materials that are used in our current commercial products, they are of polymeric nature. So you need to know some types of these materials. Specifically, hydrophilic polymers, they tend to be mucoadhesive. If the polymers are hydrophilic or water-soluble, then they tend to be mucoadhesive. If the polymers are charged, for example, all polyelectrolytes tends to be more mucoadhesive than non-ionic polymers. And also you need to know some examples of types of mucoadhesive formulations. And these types may include tablets, films, solutions, various semi-solid formulations, gels, for example. Then they could include lozenges, they could include some micro or nanoparticulate solutions, and in situ gelling systems, those that could form gel once they are administered onto a particular part of human body. You could also, in order to learn more about the mucoadhesive dosage forms and their studies, you could also sign up for my research channel, and there's several videos highlighting the recent research conducted in my research group, and it gives lots of examples of types of materials that are used as mucoadhesives and the methods used for testing these mucoadhesive materials. Then there were 2 lectures on capsules. First it was hard capsules and second was soft capsules. So you need to know the classification of pharmaceutical capsules into hard capsules and soft capsules. Then you need to know about the production and properties of gelatin. There's main factors, main materials that are used to produce gelatin, and there's 2 ways of producing gelatin depending on the source of raw materials. You need to know advantages and disadvantages and limitations of gelatin. Also, you should have an understanding why some companies manufacture capsules and others manufacture tablets. Moving on to oral transmucosal drug delivery, and what you're supposed to know on this topic is about 3 routes of drug administration in the oral cavity and the differences between them. These include buccal delivery, sublingual delivery, and gingival delivery, and there are some differences between them. For example, sublingual delivery, the membranes, sublingual membranes, are much more permeable, for example, compared to buccal membranes, and which means that the drug may get absorbed much quicker sublingually and could provide quicker onset of action. You need to know and should be able to discuss the physiological factors in the mouth. There are a number of physiological factors that could affect the dosage form and could affect the absorption in the mouth. For example, there's saliva produced in the mouth that could facilitate dissolution of a dosage form, but also could remove the dosage form from the mouth. For example, when the patient swallows, they may swallow the main part of a dosage form, which will mean that it will not get absorbed by the membranes in the mouth. Also, pH is an important factor, and you need to have understanding of a so-called pH partitioning hypothesis, which states that non-ionic molecules will get absorbed by any biological membranes much better compared to ionizable molecules, compared to ionic molecules. Also, you should have some knowledge of formulation factors. One of the factors will be polarity of the drug molecule, or log P, and you need to know what log P is, and you need to know that the log P will affect the absorption of drug molecules through the or by the biological tissues, and specifically for this particular lecture is by the tissues in the mouth. So less polar molecules will be more capable of getting absorbed. Again, another very general rule applicable to all biological membranes, not only for the oral transmucosal drug delivery. Next factor is molecule charge, so that's related to pH partitioning hypothesis I have mentioned. Next factor is molecular weight. The smaller the molecule is, then it will be easier getting absorbed by the membranes. Then you need to be able to discuss some types of formulations used for buccal drug delivery. For example, it could be buccal tablets, could be buccal patches or films. Next is rectal drug delivery. So you need to know the reasons why a rectal route of drug administration is applicable. There are a number of reasons that I mentioned in my lecture. And you need to know some details of physiological features of the rectum. For example, that there's very little amount of fluid in the rectum, which leaves very little scope for a dosage form to dissolve in there. You need to be able to discuss the types of dosage forms for rectal administration. The main dosage forms are suppositories, and so you need to have understanding how suppositories are made and what are the bases for making suppositories. And in the next lecture, covering oral modified release drug delivery systems, you need to know 3 classes of these systems, such as delayed release dosage forms, gastro-resistant dosage forms, and extended release dosage forms. Then you should have understanding of the site of actions for oral modified drug delivery systems, where the gastroretentive systems will be targeting the stomach when there will be more retained in the stomach. Small intestinal targeted systems, for example enterically coated systems, they will be protecting the drug from the acidity environment in the stomach. Once the dosage form will move to the intestine, then the pH will go up and enteric coating will come off, releasing the drug. Then colonic systems, when the systems designed to release the drug in the colon, and extended release systems that could release the drug throughout the GI tract transit. Coating of pharmaceutical dosage forms, well, there will be 3 types of coating. It will be film coating, which is typically polymer based, or sugar coating, or compression coating, 3 types. And you need to be able to discuss the reasons for coating, types of coating processes, film coating formulations and materials, and some other ingredients such as plasticizers and colorants. Then moving on to the final lecture in the series, which is focused on sterilization of pharmaceutical formulations and medical devices. What you're supposed to learn and understand in this lecture is you should understand maths of sterilization. I appreciate it is a bit more difficult, but you have to. Then you need to know main methods and principles of sterilization, and you need to know applicability of these methods, their advantages and disadvantages. You also need to know the needs for sterility, which pharmaceutical preparations, medical devices supposed to be sterilized. And also you should, as a part of the maths of sterilization, you should be familiar with the growth and reproduction of microorganisms curves and factors affecting different stages. Then specifically for maths of sterilization, you should be familiar with the equation describing the kinetics of cell inactivation, condition for guaranteed sterility. Then you should be familiar with the D value, or decimal reduction time, which is time taken to achieve 1 log reduction in the number of microorganisms. And also Z value as an increase in sterilization factor, for example temperature for steam, dose for radiation sterilization, to produce a 1 log reduction in D value for a particular microorganism. I hope you found this revision session useful. I appreciate that 12 lectures is a lot of material to go through, and this is very difficult material, so please take it seriously. If you don't understand any parts of the course, then feel free to send me an email. I will try to reply to each email in good time. And also a piece of advice, please use some other additional sources of information. Don't just rely on the lecture notes and podcasts, but also if you don't understand something, then try to find a textbook with a relevant chapter. In each lecture in some lectures I did provide some sources of information and also some web links. Good luck.